So in this video, I'm going to compare the z-test and the t-test to each other. And for the context of this video, I'm just going to do it with one sample. So we compare that one sample to the population, as opposed to two sample tests where you compare two different samples against each other, which I'll do in future videos. So starting with the z-test, what we assume firstly is that we have our population and it's normally distributed. So we know that a normal distribution can be described with the mean, which we call mu, and the standard deviation, which we call sigma. So if we pull a sample from our population, what we can expect is that the mean of our sample observations is also going to be normally distributed, and it's going to be about, call it mu x bar, so this is the mean of the sample mean, and with the standard deviation, which we call sigma x bar. Again, that's the standard deviation of the sample mean. Now, if we know both the mean and the standard deviation of our population, we can calculate these two for our sample quite easily. Let me just pop this underneath. So we know that the sample mean should be distributed around the population mean, which is mu from up here. And the standard deviation of the sample mean is equal to sigma divided by square root n, where sigma is the population standard deviation and n is the number of observations that you've drawn out in your sample. So that's what we've been playing around with for z-tests. So if we jump over to a t-test, again, we're going to start with having some population, and we can assume that it's normally distributed, and it's going to have some average value mu, which we know about. But this time, the difference is we're not going to know the standard deviation of our population. This is something that is usually quite difficult to measure anyway, so this is probably the more common case where for your population you only know the mean, you don't know the standard deviation. So what we can do is kind of follow the same kind of process. So we can draw out a sample from our population, and we know that our sample mean, I should say, should follow a distribution again. So the mean of the sample mean, again, we can use the same kind of process as here. It should be distributed around the mean of the population, which we do know. But this time we have a standard deviation that is unknown. So as a stand-in, what we use is S, x bar. So this is going to be the standard deviation of your sample's mean, specifically here, all right, which we can calculate slightly differently. It's going to be S divided by square root n. So n is the same thing, it's just the number of number of observations within your sample. But S here, that's something slightly different. This is the standard deviation of the sample that you're looking at. Okay, as opposed to back here where we knew what the standard deviation of the population was, so we could use that to find sigma x bar. So that really is the difference between these two tests. So for a z-test, you're going to know what sigma is. For a t-test, you don't know sigma. Okay, so depending on just that piece of information, that is the criteria for choosing whether you're going to do a z-test or choosing whether you're going to do a t-test. Alright, so scrolling down now, we're going to talk about converting between x bar, which is the distribution of sample mean, into both the z and t versions. So if we draw x bar, we said that it was distributed normally about a mean of mu x bar, and it has a standard deviation of sigma x bar when we're working with the z stuff. So when we convert from x bar into z, we have this equation here to help us, and all that happens is that the mean ends up going to 0 when you're in the z domain, and the standard deviation ends up getting normalized to 1. So if we then look at it in relation to t, it's the same kind of starting point where we know that x bar is normally distributed about our mean of mu x bar. But this time we don't know the sigma x bar, we only know s x bar. So when we convert it into t, we use this formula which follows very similar pattern. Got x bar and mu x bar on the top line, which is exactly the same. All that's changing here is the standard deviation. This one is calculated based on the sample. This one was calculated based on the population. So what happens when we convert it into the t-scale? We end up with the mean going to 0, just like what happened with the Z1. However, this time we don't know the standard deviation directly, and basically the t distributions are just a whole bunch of ones which look fairly normal, but the standard deviations differ. So this one here that I've tried to draw in is meant to be exactly the same as this one here, which is our standard normal. Okay, so that's where we've got a mean of 0 and standard deviation of 1. But here what we can see for this blue line is that although the mean still sits at 0, the standard deviation is bigger because we've got a wider distribution. And then again, when we go to the green one, it's even more pronounced. So we have a bigger, again, standard deviation, although it's still about the same mean value of 0. So what controls kind of which one of these curves we end up with is something called the degrees of freedom, which I've marked in here. And this really just relates to how many observations are included in your sample. So you can calculate the number of degrees of freedom as being equal to n minus 1. Remember, n is the number of observations in your sample. So what happens is if you have an infinite number of observations in your sample, you actually end up with this black line here, which is essentially the standard normal. So if you have infinite degrees of freedom, so basically infinite number in your sample. Okay, so this is our standard normal. So exactly the same then as having the Z distribution. However, you're never going to get infinite number of observations in your sample. So you're going to end up with one of these other curves, which changes as you change the number in your sample. So as you go this way, so there's more curves that sit in here between each of the ones I've drawn. This is increasing degrees of freedom. So what you can conclude from this is that as n, the number in your sample increases, the number of degrees of freedom increases, which makes sense because we said that the degrees of freedom was just equal to n take 1. And as you perform these increases, the t distribution goes toward, or you could say approaches, the Z distribution. Alright, so really the main message is that these two approaches are very, very similar to each other. All that is the main difference is that for those t distributions, the standard deviation differs depending on how many things are in your sample, as opposed to the Z distribution, where the standard deviation is always going to be equal to 1. So that's all there is in this recap video, and I'll see you in some of the examples.